let's look at a spherical insulator. That has charge throughout the entire sphere.
So on the flux, is that just like how well it's going to jump out to that point, or?
Flux is just a measure of how much field passes through an area. So our spherical insulator, let's say it's charged throughout, so the whole entire thing inside has charge. So it's going to have a volumetric charge density of rho. Again, the electric field is going to be different inside versus outside, so we need to look at both. Doesn't really matter which one we do first. Let's go ahead and look at inside. Let's say we want to know the value of the electric field at some point in here. Again, I'm just going to use a little r to represent the distance to that point. So I'm going to draw myself a Gaussian surface, an imaginary surface. It's going to be a sphere so that I can satisfy the conditions so that the flux can be simply E times A. So again, E times A, whenever you're using E times A is always, without exception, the area of the imaginary surface you've drawn, the Gaussian surface you've drawn. Okay? There's never an exception to that rule. So in this case, it's going to be 4 pi little r squared again, because we have a sphere. For the other equation for flux, Q enclosed over epsilon naught, we need to figure out how much charge is inside the little sphere. We don't need the total charge. We only need to know how much charge is inside that little sphere. So how are we going to do that?
Just rho.
We need rho. And the volume of the little sphere. We're just using the relationship that rho is charge per volume. Rho is constant, it's uniform whether we talk about the sphere as a whole or some chunk inside. So our chunk, our Q enclosed, the charge on that smaller, inside that smaller sphere is going to be our charge density times the volume of that smaller sphere. We only want to know how much charge is inside that smaller sphere, not the total charge on the entire object. Excuse me. So now we can set these equal to each other.
And before we use, right now we're using the density times the volume. Before we use the n times the volume.
That was surface charge density times area, because surface charge density is charge per area. This is volumetric charge density we have now.
So basically it's the density whether it's surface or...
Right. So the charge enclosed is always going to come by way of density. The 4 pi's cancel. This r squared cancels with 2 of these. So that leaves us with E is equal to rho r over 3 epsilon naught. This equation will work as long as r is inside the sphere. It does work at the boundary as well. It will work at the surface. By the way, no, never mind. Sorry. So we had to find out how much charge was actually located within this smaller sphere we've drawn. That's where the rho times the 4/3 pi r cubed came from. And that's what our equation simplifies to. The electric field strength will depend upon the volumetric charge density times however far we go out over 3 epsilon naught. Bless you. Outside. We want to know the field out here somewhere. I'm going to use little r still to represent the distance out to the point we're interested in. So this time, when we draw our imaginary or Gaussian surface, it's going to be bigger than the actual charged object. We're looking at the flux through that Gaussian surface. It will still be E times A, where A is 4 pi r squared, because it's still a sphere. A is always the area of the Gaussian surface. So really, the trickier part is always finding the Q enclosed. Figuring out how much charge is inside of our surface. And we're always going to find it by way of charge density. Okay? We know it's rho times volume, because we're just using this relationship here. Charge would be rho times volume. So rho times 4/3 pi, which radius do I want? Big R or little r?
Big R.
Big R this time. We're enclosing the entire charged insulator. But the charge only goes out to big R. The charge doesn't come all the way out to this imaginary surface. The surface is just that. It's imaginary. It's not an actual object. It's not charged. So if we're outside, we only need to talk about the volume of the actual object. So big R cubed is what we want. Keep in mind, rho times this 4/3 big R cubed would be the same as the total charge, Q, on the sphere. We set these equal to each other. The 4 pi cancels, but that's it. So E will equal rho times big R cubed over 3 epsilon naught little r squared.
Now wait a minute, when you did the inside, you canceled the r squared with 2 from the r
That's
cubed.
because they were the same r. This area is always the area of the imaginary surface. To find the charge inside that surface, we just needed to know the radius of it, because we only needed to know how much charge was in this little spot. We're outside now. We need to know how much charge is inside this big sphere we've drawn. Well, this entire object is charged. The charge only goes out to big R. It doesn't go all the way out to little r. That's why we have little r and big R in the same equation. Big R is a constant. Big R is the actual radius of the charged object. Little r is the point we're interested in. This equation will work outside of our sphere. Will it also work at the surface if little r was equal to big R? Look at what happens to this equation versus this equation. If little r is big R, we get rho big R over 3 epsilon naught. If little r was big R, we get rho r over 3 epsilon naught. Both equations work at the surface. This equation works at the surface, working our way outwards. This equation works at the surface, working our way inwards. It's called the boundary condition. Both equations have to give us the same value at the boundary. By the way, since this rho times 4/3 pi r cubed is the total charge on the sphere, this equation is the same thing as that. The 1 over 4 pi epsilon naught, which is k, times q, the total charge on the sphere, over r squared. It's the same thing. This is just written in terms of density. This one's in terms of the total charge.
So even with an insulator, you can count it as a point charge?
Mm-hmm. Yes. So whether it's an insulator or conductor, doesn't matter. If it's spherical, we can treat it as a point charge outside.
Outside.
This is not valid for inside, but it will work for outside. the total charge cube, right there.
So that electric field of the Gaussian surface on the inside is for every point on the surface of the fake sphere inside. Or, yeah, I guess it's at any point at that radius.
Yes. And we could certainly draw even smaller and smaller spheres with smaller and smaller radii, or bigger and bigger, until we reach the surface. So as long as you know how far away from the center you want to know the field, then you're good to go.